Hey, this is Horner, and it's part two of what you absolutely have to know about fluids. So, water fills a tube as shown. So, we have a tube. It's open on this end, but it's closed on the other end. And it's been filled with water, so we were able to get all the air out of the tube by using a special device. It says, what is the pressure at the top of the closed end of the right tube? So, notice we don't have anything pushing down on this from the outside. All we have is we just kind of have a barrier. So we're really worried about the push that's happening from this side and then pushing it back up against this end of the tube. So it's kind of like a wall if you were pushing something into a wall, same type of thing. We're going to assume that there's 1 atmosphere at the top of the open end of the left tube. So we have 1 atmosphere pressing down right here. So we're going to say that the pressure at the closed end should be equal to the pressure at a depth that is equal to a horizontal line coming all the way across. And this is 1.9 meters. We know that this is 1 meter, so the length of the water or the depth of the water at this point, which would also be at this point, is actually 0.9 meters. And because of that, we're going to say the pressure at 0.9 meters should be equal to the pressure on the closed end of this tube. That's equal to the atmospheric pressure plus rho GH. And so now we're going to put in atmospheric pressure of 1 atmosphere, which is, we said we're going to just use 100,000 pascals, make it a little bit easier. The density of water is 1,000 kilograms per cubic meter. It's also 1 gram per cubic centimeter. But because we're dealing with meters here and meters here, we need to use the kilograms per meter cubed. We take that times 9.8 and then times zero point 0.9 because we said that was the depth, and you get about 108,820 pascals. So when you do the conversion for the math, you end up with 1.09 atmospheres. So in the problem, we got this answer. That's the absolute pressure. And absolute pressure is the real pressure. That's what you would measure. There's another way to report pressure that we've talked about, and that's called gauge pressure. It's just the pressure in excess of 1 atmosphere. It's the delta pressure above 1 atmosphere. So when you measure the air pressure in your tires, you're measuring gauge pressure. Tire gauge measures 0 when you hold it out in the atmosphere. So that 0 for the gauge is actually the 1 atmosphere for the atmosphere for real pressure. So this this gauge only measures pressure greater than the 1 atmosphere. And the problem above, the gauge pressure, would be 8,820 pascals. So gauge pressure is really just this part right here. So that would be our gauge pressure. Bottom line then is absolute pressure is equal to gauge pressure plus an atmosphere. So when you're asked to find pressure, calculate the absolute pressure because that's the real pressure. Once you only calculate the gauge pressure if you want to know what it is above the 1 atmosphere or the delta pressure above the atmospheric, or are asked to find the gauge pressure. So those are the same things. There are some other units for pressure that we can use. Remember, in the physics world, physicists love to have one standard for things. So volume is a cubic meter, density is kilogram per meter cubed, pressure is Pascal, which is a Newton meter squared, mass is in kilograms, height is in meters, gravity is in meters per second squared. We'll stop there. All the physics equations are set up for that. So that means that if you use different units, you're going to get a much different answer. Many times in the real world, the units aren't very convenient. That's the case for pressure. As you've already seen, it's a lot easier to say 1 atmosphere than it is 101,325 pascals. So here are some of the more common conversions to go between different units for pressure. One is the atmosphere. That's the easiest one. It's 101,325 pascals, or about 100,000 pascals. Millimeters of mercury is another one. That's sometimes you'll see that 1 millimeter mercury is 130 pascals. An inch of mercury is what most of the weather people talk about. So you might hear 29.95 inches of mercury, and that seems to be standard pressure. In a hurricane, that can go down really low. It can get to be about 24 inches of mercury. And in a high pressure system, it might be like 31 or 32. and I'll kind of show you how this works here in just a second, but the last one is pounds per square inch, and that's what your tires on your car use. It's also what, if you play basketball, your basketball or your volleyball, when you pump those up, you want to pump them up to a certain PSI. It's usually not very high at all, but it provides lots of bounce. So let's do some applications of our pressure equation. We call this the hydrostatic pressure equation. So remember, this is absolute pressure is equal to the atmospheric pressure plus rho GH, which is the pressure at a certain depth. Or the gauge pressure. So we have a scuba diver floats 20 meters below the surface of a lake. They want to know what are the absolute pressure and the gauge pressure on the diver. So here we go. We know pressure, we know the atmospheric pressure is 1, and we know the depth that we're at is 20 meters. So we can just do our math, and we end up with an absolute pressure of 2.96 times 10 to the 5th pascals. The gauge pressure then would only be about 1.96 times 10 to the 5th pascals. So we said we were talking a little bit earlier about barometers, and we said inches of mercury. So here is a good example of a really old-fashioned barometer. So this one uses mercury, and weather reports usually give the barometric pressure. It's the pressure in the atmosphere, which varies a little bit from day to day, and its units are inches of mercury for what we see in the United States. So what is the barometer and what are inches of mercury? So the original barometer was just a long test tube. They filled it with mercury and then they turned it upside down. And when they did that, some of it would leak out, and you get a vacuum gap at the top. So there's no air in here. It's just a vacuum. As the atmosphere presses down on the outside, then we say the pressure is going up and you would see the column of mercury rise. When the pressure of the atmosphere isn't as big, so maybe we get, instead of long red arrows, we get little blue arrows, then it won't go up as much. And so that is the diagram, kind of what you do. So they want to know, why doesn't all that mercury flow out? And it's because we have at point A, we have the atmosphere pushing down. Okay, so the pressure at point B must be equal to the pressure at point A. So the only reason for that to happen is B needs to be equal to the original pressure plus rho GH, but because we have this vacuum, we don't have any pressure up there. So now we can say that the pressure at B is really just the density of the fluid times gravity times the height, and our height there is 0.75 meters. 1 atmosphere is about 750 millimeters of mercury, so that's about 29.5 inches of mercury. So inches of mercury is just one way to measure pressure. All that mercury can't flow out of the tube, mainly because there isn't any pressure in the top, or put another way, the mercury stays in the tube because there is an equilibrium of pressure. So the atmospheric pressure A pushes and holds the mercury up into the tube. So here we can kind of see the same type of thing where we go through and actually solve. So we've got the pressure at A should be equal to the pressure at B. Because we have a vacuum, that pressure at B is equal to, this would be the atmospheric pressure, but there isn't any because it's empty at the top, plus rho GH. We know that the pressure of mercury is about the density of mercury is 13,600 kilograms per cubic meter. We know gravity is 9.8. And so if you plug those two things in together, and we use standard atmospheric pressure, which is really 101,325, but we're going to use 100,000 here. You solve for height, and you'll get 0.75 meters, 750 millimeters of mercury, or 29.5 inches. So that is where the barometric pressure in meteorology comes from. There's another thing here called a manometer. And gas pressure can be measured using this U-tube, and it's filled with a liquid, and we call that thing a manometer. One side is filled, then there's a chamber of gas over here, and if the gas has a pressure greater than atmospheric pressure, it'll push it up the other side, so you kind of see that. And this is another way to go through and measure atmospheric pressure. So if fluid is pushed up the tube due to the gas pressure, we can assume the fluid is water. If we do that, we have atmospheric pressure of 100,000 plus rho GH. It's 1,000 times 9.8. And here we've got a column that is 20 centimeters tall, to from the top down to where the liquid would be level. And so we put in that 0.2 and you get 101,960 pascals. So let's take a look at blood pressure and IVs. So if you've ever had an IV, you notice they hang the bag above you. If they put the bag below you, instead of the fluid flowing into your body, you actually have blood flow out of your arm and starts to creep its way in the tube back to the IV bag. I was in the hospital one time and they did that. I think on accident, but you could see the blood flowing back and it was a little unnerving. Anyway, you can a reasonably good blood pressure is somewhere around 120 over 80. It's 120 millimeters of mercury over 80 millimeters of mercury. So what in the world does that mean? That means that when your heart beats and pumps blood through your circulatory system, your blood pressure reaches a maximum of 120. When your heart's at rest, your blood pressure drops to about 80. These are gauge pressure readings, so these are not atmospheric pressure readings, so this is really important. So when you're standing up, where is the blood pressure the greatest? So let's say that you're sick in the hospital and because you're sick in the hospital, they give you an IV. An IV is bagged just fluid or medicine or blood. They want to get into your body. So to do this, they insert a tube that's attached to the IV bag into one of your veins. They hang the IV on the stand. And why do they do that? Because the IV bag then pushes its way into your body because it's elevated. So when you are standing up, here's the question: where's your blood pressure the greatest? It should be at your feet. And that's because the greater height of blood above your feet is pushing down on your feet. So we can just say that's equal to rho GH. And the greatest height is going to be from the top of your head all the way down to where your lovely feet are. So there they are. Number 6, an accident victim needs blood. How high must the IV bag of blood be elevated to enter the person's body? So we can assume the blood pressure is 120 millimeters of mercury over 80 millimeters of mercury. So let's go ahead and solve this one. It says we know that the pressure at the bottom of the IV tube must be at least equal to the rest blood pressure of the accident victim. So we know it needs to be at least 80 millimeters of mercury. So, and we got to remember this is a gauge pressure, so I'm going to just put PG. So the gauge pressure here needs to be equal to the pressure of the rest blood. So this is the blood that's quote unquote at rest. So the resting blood pressure of the victim. So this is the gauge pressure of the IV. So we know that that's equal to rho times G times H, the height of IV, needs to be equal to 80 millimeters of mercury. But remember, we don't want to use that. We want to use pascals. So there's 130 pascals in that 1 millimeter of mercury. And so we end up with 10,400 pascals. The density of blood, so the density of blood, so this is for blood, is somewhere around 1,050 kilograms per meter cube, so it's thicker than water, which makes sense. We'll use 9.8 for gravity, meters per second squared, and then the height of the IV, and that should be equal to 10,400 pascals. So if that's right, the height of the IV should be 1.01 meters, which is just a little bit greater than 3 feet. So that's why the IV stands are so tall. And you don't need to look at the end of the study guide because you already have this answer. That's probably a good place to stop, and we'll go ahead and do part 3 in the next video.